Okay then, so we said in the last video that we can use coding, and you're going to see here an example where it's sort of forced to use it. So we've got something that's normally distributed here. We've got this value, we've got this. Okay, so we know now that when we see neat probabilities, we think that the table might be involved, and such is the case here again. It's said that it's larger than 20, so we do want the positive value here. So the value that lines up with 0.2 being above for the Z value is 0.8416. We've got then an X, we've got its corresponding Z value, and we've got a standard deviation there. So when we think the code is involved, we write it out. We can use an X and its corresponding Z. So this is going to be 0.8416 equals 20 minus mu, which we don't know, over 3. Okay, so that's an example. That's an example there where we can then quickly find out our mu value. All right, so in the interest of completeness, let me just quickly find that out. 3 times 0.8416, and then 20 minus that answer. So 17. I think I've done something wrong, haven't I? No, I haven't. So 17.4752. Okay, it makes sense because if that's 17-ish, 20, 0.2, yeah, that makes sense. So let's do another one. In this one, what do we got? So we've got normal with 50 and unknown standard deviation. Less than 46 equals this. Find the value. Okay. So not immediately obvious what to do for this one. Quick scan of my values. No, I'm not quite sure. Okay, so I've got a diagram there. Well, shall we use the code again? So let's see what I can do with this one here. So X, my piece of data is 46, isn't it? So 46 minus, right, I don't know the mean, do I? So what am I going to do on this? Sorry, let me just grab my notes. Okay, so I've got 46 minus mu over the standard deviation. Oh no, sorry, I do know the mean. It's 50, isn't it? Over this one here equals Z. Now, I'm a bit blocked from here in terms of doing anything because I need my Z to find my standard deviation. I need my Z to find my standard deviation, or my standard deviation to find the Z value that this corresponds with. But we can do something. The piece of data that we haven't used yet is this. So the clever idea is that this 0.2119, so it says being less than 46, this 0.2119, well, there is a Z value that corresponds. This is an X value, right? So this is saying 46, but I could find this Z value using my calculator. So if I did the inverse normal on my calculator, I could use the fact that on the inverse normal, mu is 0 and the standard deviation is 1. This is always true, by the way, okay? So I could do this on my calculator with 0.2119. And what it will do is it will tell me the Z value that makes it so that the probability is 0.2119. So when I do that, I get minus 0. It's approximately minus 0.80. So this is where things kind of break open. So just to recap, I'm using the fact that being less than 46 is this probability. Well, there is also a Z value version of saying the same thing. And if I use my calculator and I use the inverse normal mode, I can use the fact that the standard normal always has a mean of 0 and a standard deviation of 1. I can use that to find the Z value, and then it means that I can sub this value in here. Okay, and you can now see I've only got one piece of information that I haven't found out. So I can work from here to finding out my standard deviation, and it should give me 5. Okay, so you've got to do a bit of problem solving there, really. It's not obvious straight away because I'm trying to work out what I've got in front of me. Using the code helps me work out what I've got in front of me. I'm also looking at this table because I'm thinking, well, maybe what they're saying matches up neatly with one of these values, but I couldn't see that value in my table. So the final thing that I fell back on is the calculator, and knowing that I can do inverse normal with the standard normal distribution as well. Okay, find the 90th percentile. Well, once you've done everything, it's like this is quite a standard question, okay? Because you can just say x is normally distributed with 50 and 5, because we know this number now. What's the 90th percentile? So again, this is inverse normal, isn't it? This is inverse normal with 0.9, and that should give you 56.4. Okay, so when you find yourself struggling, and you will, yeah, you got to go through the steps. If you think the coding's useful, check your table, draw a diagram, and the really clever idea here was that the 0.2119 works for 46, but it also works for a Z value, which we were able to find out. So we've got another question here, which I think is going to make us do something different. Let's have a go. So the time to fly from London, do I have, let me just check if I've got the table somewhere. Do I have the time taken? Yeah, okay. So the time taken from London to Berlin has a normal distribution with mean of 100, yeah. And standard deviation is unknown. Given that 15% of the flights take longer than 115, find the standard deviation. Okay, so what could we do? Two approaches, really. One, it said 15% take longer, so that seems like a neat number, so I'm going to check the table for that first. That's the value, isn't it? So 15% corresponds to 1.0364. So I'm going to write the code because I think the coding might be useful. So 1.0364. 15% also, that's the x value that makes it happen. So 115 minus 100, there we go. Okay, so if I do 1.0364 equals 15 over mu, and I swap them around, I get 14.5. Okay, so that would be a table question, yeah? Let's do this one here. So we've got mu and sigma both missing. So what do we got? Less than 160 is 0.99. Well, that means that 160 is way over here then, no? Because it means all of that is 0.99. Which also means that this is 0.01. That sounds like a value that would be in the table. Yep, there it is. So so I'm going to write x equals, I'm going to write z equals 2.3263. Okay, Greater than 152 is 0.9. So that's somewhere here maybe. 152 is 0.9. Okay, so that would mean that you have 0.1 below you. So what I need to do is I need to take the 0.1 above and make it negative. So that's the 0.1 above, and because it's on the left, it needs to be negative. So let's do, what was that? Minus 1.2816. Yeah. Okay, and actually here there's enough information now to find out the mean and the standard deviation. If I write the code, so let's write it here first. So here we're going to do 2.3263 equals 160 minus mu over the standard deviation. Then a lot of people tend to do this. Just check you're happy with that rearrangement. I've multiplied by lambda and I've added mu to both sides. Same over here. So z equals x minus mu over this. So minus 1.2816 equals 152 minus mean. It's the same mean and the same standard deviation in both parts. So if I do the same thing here, mu, yeah, minus 1.2816 sigma equals 152. Okay, so can you see it yet? It's a bit like an x and a y, an x and a y. It's simultaneous equations, so they can be solved simultaneously. If you do this, you must make sure that the level of accuracy is high enough, okay? But it is sufficient to solve on a calculator as long as it's accurate enough beforehand. The technique is obvious, okay? You can then use actually a calculator to do the final part. And I'll just get my values for that. So where are my values? So we're looking for a standard deviation that rounds to 2.22. So you should get 2.21 and a bunch there. Do not write 2.21, okay? If it rounds to 2.22, then that's what they're looking for, okay? Be really careful with your rounding on this question. The mu ends up being 154.84 ... So 155 or better is what they're looking for on that one. So please be careful with your technique on this in terms of lots of accuracy. When I've marked this one in the past, it's when people don't write enough decimal places that they can lose marks on this one. But yeah, there you go. It's quite nice with the diagram, nice way to do it. And you do coding twice. It's actually a really nice question and is often quite well answered on the real paper. So one more time, you've got a question here to have a go at with this idea of when both mu and standard deviation are missing. Okay, so to show that, I'm not going to go over that part there again. For part B, you should end up getting something equivalent to 286 minus mu equals 1.0364 sigma. Yep. And then again, the idea will be that you solve A and B again. This is an old spec question. You can tell it's old spec as well because do you see the mention here of 68.3%? That's the idea of being sort of one standard deviation above and one below, okay? So for D, what you would just do is you'd find the mean, you'd add on and you'd subtract a standard deviation. So for D, the answer should be 251 and 285, okay? It's that interval. Okay, there we go.